Welcome to qnawire.
This is problem 68 of chapter 23. In this problem, we are asked to describe why is it that optical devices using visible light, are not able to resolve objects at atomic scales, or why we can't use visible light to resolve atoms. So let's start with the equation of Airy's disk. So here we have sine of theta equal to 1.22 lambda over d. So let's take a moment to appreciate this equation. Here we have sine of theta, where theta is the angle from the central maximum to the first dark band, or that disk surrounding the resolution, of light coming from a hole of diameter d using wavelength lambda. So if we are looking at objects on the size of atoms, or atoms themselves, let's treat the atom itself as a source of the light coming to our device. So if we treat the atoms themselves as our source of light, or our aperture, we can say that D, capital D, is on the order of 1 angstrom. So 1 angstrom, which is equal to 10 to the negative 10 meters. So angstrom is a unit used for interatomic distances, so this is the appropriate unit here for this problem, for distances between atoms or atoms themselves. So we're going to use approximately 10 to the negative 10 here for this capital D. For lambda, we are limited to 380 nanometers for the smaller wavelengths, and then lambda, we're going to call this lambda vis because this is the limit for visible light, 740 nanometers. So notice that the wavelength is on the order of nanometers, whereas the denominator is going to be on the order of 10 to the negative 10. So let's see what happens if we pick an average wavelength here. So let's pick an average wavelength. Well, let's be optimistic and let's try to choose the smallest wavelength that we can. But you're free to choose any wavelength here. The result is still going to be the same. Let's go ahead and calculate sine of theta. Let's suppose we go on the lower end. Here we're using violet, or maybe even ultraviolet light here. 1.22 times 308. Let's go to meters. So this is going to be times 10 to the negative 9 meters. Here in the numerator, here in the denominator, we're going to have 10 to the negative 10 meters. Let's see what this comes out to be. Again, notice that this power is going to go to the numerator, and this is going to go to the denominator. We're going to have a factor of 10 here, 10 times this. So you can see that the result is going to be greater than 1. So why is that significant? So here, before we do that, let's go ahead and let's get an exact number. Well, we already know that it's going to be greater than 1. Here, when we evaluate this, we get 4,636. Meters cancels out with meters, so this is just a number. Sine of theta, there is no theta such that sine of theta is equal to this number, because sine of theta is bounded by negative 1 on one end and 1 on the other end. So sine must be between these two values, because that's what the sine function, that's how it's defined to be. It's between these two values. It oscillates between these two. Here we have a number that's way bigger than 1, so there is no angle theta to produce this number. What this means physically is that there is no angle such that that first dark band is found. So if we're trying to look at atoms with visible light, we're just going to see brightness. We're not going to see that defined outline. because to resolve an object, we need that dark band so we could contrast and we can know where the object ends, where it begins. There must be some definition of at least an outline. Here, there is no theta to produce that. So given the distance here, if light is coming from this atom, if we're using light that's visible, so we take these type of wavelengths, whatever number you pick between here for lambda vis, it's going to produce something similar because of the orders here. The order for capital D is on the order of 10 to the negative 10. The order for visible light is in nanometers. So you're going to get something greater than 1. The result is going to be the same. There is no angle so that you could distinguish that first order diffraction pattern necessary to produce an image. What you're going to see is complete brightness, which is the same thing as not seeing the object at all. Okay, so this concludes problem number 68.